Welcome back. In the last module, we looked at the exponential function y equals e to the x, which had the special property that its derivative is also e to the x. In this follow-up module, we shall employ variations of the exponential function to model real-world phenomena. Consider the following function f, where a and k are arbitrary constants. Differentiating f using a method we shall learn in day 10, we get the following. Notice that this equals k times the function f itself. Therefore, we have shown that f and its derivative f' differ by a constant multiple k. In other words, the derivative of f is equal to itself multiplied by a constant. Terminology-wise, we say that f' is proportional to f. In the real world, there exist many natural phenomena where the rate of change of a quantity is proportional to itself. Therefore, the function f serves as an excellent mathematical model for such situations. In fact, such is the importance of the function f that we give it a special name, the general exponential function. Terminology-wise, a is called the initial constant, and k is called the proportionality constant. Here are some graphs that arise from the general exponential function by varying a and k. Notice that the exponential function e to the x is simply the special case when both a and k are equal to 1. By changing k, you modify the steepness and orientation of e to the x. Specifically, as you increase k, the steepness of the graph increases, as you can observe from the graph of e to the 2x. And if k is negative, the graph becomes reflected about the y-axis, as you can see from the graph of e to the minus x. Finally, observe that the constant a serves as the graph's y-intercept, as you can see from the graph of 2 times e to the x, which moves the y-intercept from 1 to 2. Let's now consider some applications of the general exponential function. When the proportionality constant k is positive, f is set to describe exponential growth. A good example of this is population growth. Consider an outback town whose population is growing exponentially according to the following model, where the value of t represents the number of years after the year 2000. Then what was the population in the years 2000 and 2010, and what will the population be in the year 2020? Regarding the function p of t in the form of the general exponential function, the value of the initial constant a is 1000, and the value of k is 0.2. Since t is the number of years after the year 2000, the population in 2000 therefore corresponds to t equals 0. Hence the population is given by p of 0. Substituting t to be 0, we get the following. And this simplifies to 1000 times e to the power of 0. Since e to the 0 is 1, this simplifies to just 1000, which you may have noticed is the initial constant a. So the initial population when t equals 0 is simply equal to a, which is the precise reason why a is called the initial constant. Moving on, the year 2010 corresponds to t equals 10. And so the population is given by p of 10, which turns out to be 7,389. Hence the population has increased more than 7-fold in the 10 years from 2000 to 2010. We can use the model to project what the population will be in 2020. P of 20 yields roughly 55,000, and so the town population is expected to explode to roughly 55,000 people by 2020. When k is negative, the general exponential function is said to describe exponential decay. A good example of this is the decomposition of radioactive material, whose rate of decay is proportional to how much of the stuff is left. For instance, consider the following model for the decay of radioactive carbon, where T represents the number of years after the year 2000. What's the initial amount, and how much will be left in the year 3000? The initial amount is given by the constant A, which is 25 kilograms. In the year 3000, the amount of material left will be A of 1000, which turns out to be roughly 22 kilograms. This shows that even after 1,000 years, we've still got around 90% of the material left. Here's a summary of what we've learnt in this module.